second lecture by Pavan Mardešić, who is going to talk about Darboux relative exactness and pseudo-Abelian integrals.
Thank you. Thank you very much, Hossein. So I'm very happy to be here. Thank you for the invitation. I must say this is the first time I'm in IMPA, first time in Brazil, and I'm very happy to be here. And I would say also that it's kind of special, for me it's quite special because I heard so much about IMPA, and my beginning of my career, my very beginning of the career was very strongly somehow connected with IMPA, even if I was never here. But somehow at that time in ICTP in Trieste, there was a sequence of schools organized by Pallis and Zeeman. And for me, these schools were extremely important. I attended several of them. And so there were lectures of Pallis, of Camacho, Linsneto, and Paulo Sad from IMPA. And so, I mean, I met these people. There was, this is Ricardo Magnet's salon. And I listened also his lectures during these conferences in Trieste. So I'm happy to be here. What I would like to speak about is a joint work. So I will write the title. So Darboux relative exactness and pseudo-Abelian integrals. So it is a joint work. Colin Christopher. And myself. So there will be, it is a long work. I think the ideas are quite simple to explain, but it's also quite technical work. For me, it is kind of difficult to say whether to say if it is a recent work or an old work, because actually the work started and was somehow we had the first draft 15 years ago when I visited Colin in Plymouth, but somehow we didn't find the time, the energy to do all the technical details, and so unfortunately the work somehow remained in some. In such a shape for 15 years. I spoke, and Colin, I think also, in several conferences about the results from this paper, and we now tried to finish the preprint to have it ready for this conference. We didn't quite succeed, but we do have some preliminary notes which we sent to Hossein, and we authorized him to distribute it among the participants of the conference. It is not for general distribution because we hope to somehow to finish a true version, which we will submit recently, but it is not yet the final version of the work. So the whole work is very much inspired by the Hamiltonian case. The introduction, which the lecture given by Ljubomir was a very good introduction to what I'm going to speak about. You have these centers in quadratic vector space, and there are several strata. I will not enter in the polemic if there are 4 or 5 strata, but there is a Hamiltonian stratum, and there are what Ljubomir calls logarithmic strata. And so this Darboux is the same thing as logarithmic. We prefer to call it Darboux. But so everything is very much inspired by the work of essentially Ilyashenko in the Hamiltonian case. So introduction. So I will very briefly say some results concerning the Hamiltonian case. There are essentially 4 results. I will not give the details. They will be given by Colin. Yes, so there are 4 results in the Hamiltonian case, which are well known. And we will try to, what we did is transport these results to the Darboux case. So these results, what is it? One studies f polynomial. One studies foliation df equal to 0 and its deformation and what we are interested in is in the creation so in order to do it, there is one first question. Yes, one supposes that this family, this function, one can have, I don't know, a picture like this, that it has a family of, it has a center here, and a family of closed circles, surrounded by a family of trajectories delta of theta. And the question is, what happens with this situation when one deforms it, when one performs such a deformation epsilon? So the first problem is the infinitesimal and tangential so when one tangential center problem. So when one starts, so we assume that f has a center, so df equals 0 has a center. And the question is this center preserved? So infinitesimal problem is, so what deformations eta preserve the center? So when I say preserve the center, this means that when you add this epsilon eta, this center, of course, it can move slightly, but you still have a family of closed orbits, you still have a center. The way how to study it is to study the displacement function, delta epsilon of t, which is a function sum mi of t, epsilon I goes from 1 to infinity. And of course, one preserves a center. This is equivalent to mi is identically equal to 0 for every I. In order to have all these coefficients equal to 0, one must have to start with the first coefficient equal to 0. This is the coefficient m1 equal to 0. So this is what we call a tangential or first order center problem. So this M1, it is, I think, known from Poincaré and Pontriagin that M1 is given as an integral along this family of cycles, delta of t, which belong to f minus 1 of t, of this form eta. And so this is given by the condition that this term is identically equal to 0. So then the question is somehow to characterize eta, all eta, such that either all of these coefficients are equal to 0. This is the infinitesimal problem. And the tangential problem is characterized all eta such that M1 is identically equal to 0. And this was, okay, so there is one, is it clear what is tangential center problem?
Are you going to define the displacement function? Or
Maybe you are right, maybe I should define it. No, so the displacement function is, so on this transversal, so the displacement function, it is Poincaré first return map minus the identity. So one considers this, maybe I should make a bigger picture. So one has this center. Here is in the middle of the center. One takes a transversal, sigma, which is parameterized by the values of the first integral. And when you deform, so these in white are the trajectories of the non-deformed of the Hamiltonian system. And when we perturb it slightly, then such a trajectory might come here. This is the trajectory of the deformed system. And this displacement, this part here, this is this delta epsilon of t. This is the displacement. And so what we are essentially interested in is the principal term, the first term, the term with epsilon equal to 1. We call it tangential because it is somehow first order as a derivative, as a tangent. Okay, and so there is one very simple case, one very simple solution of this problem. So it is, if you take eta, which is equal g df plus dr, with, for instance, g and r polynomials, then, of course, the integral among delta of this form eta is identically equal to 0. So why is this the case? So the reason is very simple, because you have, as delta belongs to a level curve, so this is in f minus 1 of t, this means that df is equal to 0 on this curve, so there is no contribution of this term, and this is an exact term, so there is no contribution. So this is trivial. The question is the converse. And this is somehow the main theorem of Ilyashenko that we use and which inspired our work. So theorem so under generic condition, on f. So this, recall me that this was the first function m1 in this development. So m1 is identically equal to 0 if and only if the form eta is Darboux relatively exact, where this precisely, if you have such an expression, this is the definition of a Darboux relatively exact form. Why Darboux? It is the same person, but who did different things. It has nothing to do with the motivation. Sorry. No, it's not Darboux. You're right. It is relatively exact. This is relatively exact, and then I will introduce in a moment Darboux relatively exact. Thank you. Thank you. Okay, so this is somehow the first problem. Sorry? maybe it is Ilyashenko. Yes. One could say, yes. You're right. Okay. So this theorem has 3 consequences. I will just be very brief in these consequences. So this is somehow the first point, 1.1. Then 1.2 is Francoise algorithm. So what is Francoise algorithm? So it is an algorithm for calculating the first non-zero. I didn't say that these functions are called Melnikov functions. MI, where did I first write them? Here. These functions are called Melnikov functions. The first non-zero Melnikov function. What can happen? It can happen that M1 is equal to 0. If M1 is equal to 0, you want to see what is M2. If M2 is equal to 0, you want to see M3 and so on until you find the first non-zero Melnikov function. And this is, so there is an algorithm which is based on this relative exactness expression. I will not speak about it. I believe that Hussein will speak about it in his talk this afternoon. So third consequence, second consequence, but third result is lower bound for the number of limit cycles, which can be born from Hamiltonian so this is a result, so it appears in the paper of Ilyashenko, and also there is a paper by Khovanskaya, and they give a bound for a lower bound for the number of limit cycles appearing by these deformations. And this number, it is essentially the dimension of the space of all deformations concerning the first Melnikov function, the Melnikov function M1. So knowing that one has to work somehow modulo relatively exact forms, you have some calculations of dimension that you can do, and you see how many forms you have, and you have the dimension, and then you can see at least how many limit cycles one can obtain. So this is Ilyashenko and Khovanskaya. I don't know if Khovanskaya is related to Khovansky or it's... Yes. Okay. And so the third result, which can be obtained from the result from this result, is that Hamiltonian systems form an irreducible component in the space of centers. So this is also relates to the talk by Ljubomir. So one of the components, one of the reducible components is given by Hamiltonian systems, and this can be proved somehow using this relative exactness expression. So this was the introduction, And now I was somehow too impatient to introduce Darboux, but now Darboux comes into the game. So now what we worked on is Darboux first integrals. So what we take f, which is equal to a product fi lambda I goes from 0 to d. M is the product of fi. So these fi are real polynomials. It is not essential, but kind of convenient. And we take lambda I, which are real. And we consider the form omega, which is equal to m df over f. So this form omega, so this is called a Darboux first integral, which is also called logarithmic first integral. So I think that we don't use the same terminology. On one hand, we, and on the other hand, for instance, Lyubomir and Hussein, they call it logarithmic, but it's a question of taste. And so, of course, yes, we assume that delta is a delta of t is a vanishing cycle at P, which does not belong to f minus 1 of t, f minus 1 of 0. So this, maybe just to make a picture, somehow maybe the simplest picture is such a picture. We have these fi are polynomials, so these, there are some curves given by fi equal to 0. These curves, we call them separatrices. And we assume that here we have a vanishing cycle. So I want to say it is a real vanishing cycle. I mean, because everything is real, so it is a family of real vanishing cycles like this, which vanish at a point like this. So here we have that this P is a center. And what we are interested in is deformations of this family. So we take omega plus epsilon eta equal to 0. Let me say also, yes, in this case, exactly as in the Hamiltonian case, one considers the displacement functions, delta epsilon of t, which is the sum of mi of t epsilon to the power I. And let me just give the formula for the first Melnikov function in this case. So this is the integral along delta of t of eta divided by m. And we address the 4 problems which appear here in the context of in the context of Darboux systems. And under some generic conditions, we will prove 4 theorems. Actually, this will be, we will have a theorem which is the equivalent of this theorem, and this theorem will have 3 corollaries which are the equivalent of these 3 corollaries. So now, we have a sequence of 4 lectures. So today I will present the theorem, the first theorem, and the idea of the proof of this theorem. Then Colin will present the three corollaries and give the precise proof of the theorem in a special case, in the case where the separatrices are lines. And in the last lecture, I plan to show the more in detail how this line case can be extended to the general case. I think it's a good place to ask questions if you have some questions. Yes? Is
real coefficient really important?
No. Real coefficient is not important at all. This, I think, is important. So this is important, and this is not important. This is just for convenience to draw a picture. The only thing we really need is that the cycle delta does not wind around this, the separatrices, which in the real picture is kind of trivial. And we also somehow, we hesitated what to put as an assumption, but in the paper of Ilyashenko, it is real. So we copied somehow his assumption. But it is not essential. Okay, so we have so as we had here the notion of relative exactness, like this, we have an equivalent notion in the Darboux situation. So a form eta over m is Darboux relatively exact if there exist polynomials P and R and constants AI such that eta over m. So why do I look at eta over m? It might be eta is a polynomial. Why do I look at eta over m? Because the first Melnikov function is given as an integral of eta over m. So we are interested in this when does m1 vanish? When is this equal to 0? So eta over m is p over m df over f plus d of r over m plus some ai dfi over fi. So the first obvious remark, so this is Darboux relatively exact. Yes. So first remark, if eta over m is Darboux relatively exact, then integral of eta over m along delta of t is identically equal to 0. The reason is the same as before. So this term, this is d of the logarithm if f is constant. So this is constant, this is exact, and this is, here we use precisely the hypothesis that delta doesn't wind around the separatrices. So this term is also 0, and we get 0. Okay, and what we are interested in is the converse. Yes?
So you do not assume any bound on the degree of f?
No. Any polynomial. But we do have some generic hypotheses, which I will formulate now. So as in Ilyashenko's work, we complexify. And we will denote by, so f, we consider f as a function on where it can be defined on a part of CP2 with values in CP1. There are some points where we have indeterminacy points. I will come to that in a moment. We complexify, and we consider Li subset of CP2 given by Fi equal to 0. And so conditions. So there are three conditions which we call genericity conditions. So the first condition is Li are smooth, and together with the line at infinity, which we denote by L infinity, intersect 2 by 2 transversally and no 3 intersect at the same point. The second condition all exponents lambda I over lambda j, lambda I and lambda j are the exponents which appear in the Darboux first integral. So this one here. All the exponents are irrational. And sum of lambda I is different from 0. And first, the third condition is the critical values. So all critical values of f corresponding to singular points or critical point in f different from 0 are lying on different levels of f. So these are the hypotheses, and the theorem is the following: the equivalent of the solution of the tangential center problem by Ilyashenko. So this is the main theorem. Assume f equal product fi lambda I verifies G1 to G3. So I will not recall m, delta, and so on. Then integral along eta over mk along delta t is identically equal to 0 if and only if eta over mk is equal p over m k plus 1 omega plus d of r over m to the power k plus some ai dfi over fi. I goes from 0 to L. No, I didn't put, okay, let me go from 0 to L. So this is the main theorem. So let me say that, so there is a recent preprint by Hossein and Ljubomir. So Gavrilov. Gavrilov and Movazati, which is in the conclusion is similar, but what is different is that fi are linear and quotients. So it is just the opposite. The quotients are not irrational, but so exponents lambda e belong to n, and lambda I over lambda j. Yeah, no, so I mean they belong to n, and then one can say that the quotients. So hence, they assume also that they are coprime. But what is somehow more interesting in order to compare the two theorems, is that hence lambda I over lambda j are rational. So this is somehow, formally there is no intersection of the two theorems, and the proof is it's certainly not the same proof. It is somehow different proof. So this was somehow introduction and the main result. Now let me say some words about the idea of the proof. Are there some questions before? Okay, so the idea of the proof is, I will first write it very, very sketchy. So first, complexify. Solve locally at a node at infinity. Transport integrate, and finally extend. Yes, maybe I should say one word. So why do we do here mk? So as far as the tangential center problem is concerned, we should take here k equal 1. So why do we take here any value of k? The reason is that for the Francoise algorithm, we need higher powers of k. And it is somehow the same cost to do it for k equal 1 or for any k. And then somehow this is the form of the theorem which would be convenient to obtain a generalization of the Francoise algorithm in this case. Okay. So as I said, one direction is somehow trivial if one has a form. I mean, I commented it for k equal 1, but it works for any k. If you have this form, if you integrate it, you obtain 0. So the important direction is this. This is non-trivial. So the idea is you start with this expression, and you must solve this equation. So in this equation, somehow the first thing, so you have to find this function, and this constant. So this constant, it is easy. So the first thing is, as I say, we solve locally at a node. So we must somehow show, we must find a node. So how do we find a node? So find a node. This is not difficult. So first we have the assumption some lambda I is different from 0, but we can assume that some lambda I is positive. This is, if not, take 1 over f instead of f. So this is somehow, this is trivial. This is just for convenience in order not to be, not to have to distinguish different cases. So we have that this term is positive, and this means that there exists some of the lambda I which is strictly positive, and we can assume that lambda 0 is positive. And so lambda 0 corresponding to L0 is positive. No, lambda 0, yes, lambda 0 is, and it corresponds to the separatrix L0. And so this means that somehow in our complexified picture, so this is CP2, we have some L0, and here it will arrive at a node. Here we have a node at this point. This is a point P0, which is equal to L0 intersection 2 with L infinity. So once we have fixed this L0, what do? We have other somehow separatrices which they are polynomials, they are somehow algebraic curves, they intersect at some points. Everything is complexified. And so we put these AIs. This is just the residues. So we put A0 equals 0, and Li and AI is the residue at Pi of the form eta, where Pi is the intersection point L0 with the curve Li, with the separatrix Li. Okay, and we work with eta tilde, it's eta divided by mk, minus sum of ai, I goes from 0 to L, dfi over fi. So now somehow these curves, they will not have a residue at these fi's. As we had that the integral along delta of eta is identically equal to 0, as delta does not wind around Li. We have that this contribution, there is no contribution here, so this is the same thing as integral along delta of eta tilde is equal to 0. So these are these AIs. And now we have to find, essentially the game will be to construct this function. This is the function that we search for. So we search I restrict to L, maybe I should, I will write it better. I restrict to L0, and so it cuts. So I mean, locally this picture is, this is like a C, and we have somehow this curve which cuts it at the point P0, and we look at the residue at this point. So we search for the function G in the formula in, I will call this formula D for Darboux. So the idea is we first will construct the function G here in the neighborhood of this point. The reason why we are able to do it is, so there are, I mean, I think two ways how to do it. One way is, so what is important is that here locally f is of the form x to the lambda divided by y. It is a very simple expression. And using this simple expression, one plugs in the form eta in local coordinates, and one can integrate term by term. And precisely the fact that one has a node has the consequence that we cannot have small divisors. So if we had, if lambda, so our lambda here is positive. This exponent is positive. This exponent lambda is precisely this guy, this sum, which is positive. So here, the fact that this is positive, in the denominator we will not have, we cannot have small denominators, and we can show convergence of the formal solution. And so we get G by local integration in a neighborhood of this point P0. Now, we want to extend this G and show that it is a meromorphic function on the call complex domain. So this is done in two steps. So the first step is to extend this function in a certain way to a neighborhood of this line. So this is somehow step number one, to extend it in the neighborhood of this point. Then one extends it in a neighborhood of this line in CP2. And then this is somehow a general theorem, the Stein extension theorem, which gives you the existence of the extension of this meromorphic function to the complement of this set. I will say it more precisely in a moment. But somehow our first aim is, once we have a function defined here, to extend it in some way in this neighborhood. So how do we extend it? Essentially, the idea is that we have to solve a sequence of equations. So let me make a new picture. So this is a somehow bigger picture. So this is my L0, which I now draw as as a complex surface. And if one has some other line, so this is L0 and this is some Li. Yes, so what do we do? Once we have a function here, the function g defined here, we take a transversal, which I will denote by sigma. And we want somehow to extend by integration this, the function g from sigma to the whole place. But we have to take into account what happens when we wind around these separatrices. This is precisely what Gavrilo mentioned as holonomy. So we have a holonomy, it's called a homological equation, which is, so here we have this sigma, and we take a path here, and we have to lift this path somehow here, and the condition is that we have that g of gamma q. So we start at the point q. Starting at the point q, this is analytic continuation of g. And what we need is that g of gamma q of p minus g of q should be the integral along eta tilde of gamma q. So the continuous extension of the function g should precisely, somehow g is given by integration. So we pass this form to the other side. This is our eta tilde. This term, when we integrate in the leaves of the foliation, it doesn't contribute anything because it is in the leaf. So somehow this function g we are searching for, it's kind of a primitive of the form eta tilde. So this primitive, we must have that when we wind like this, we arrive at a point, the difference from the starting point and the final point, it must be precisely this integral. So this is something that we denote by variation along gamma q of g. So we have the equation variation gamma q of g is equal to this integral along gamma q of eta tilde. I think my time is up, but I will at least say one more thing. So what is the essential idea? In order to obtain, so this must be true for all paths. And so what do we do? How do we obtain that this is true for all paths? We have some compatibility conditions which assure this. What are the compatibility conditions that we need? These compatibility conditions are the vanishing on some cycles. It is the same philosophy as in Ilyashenko's work. So in Ilyashenko's work, how does it work? You take your cycle, and under the genericity conditions, he shows that he generates all the cycles of the foliation. And the problem is that there the cycles are the vanishing cycles. And here we don't have sufficiently vanishing cycles. So here somehow the key of the story are Pochamer cycles, which is the same thing as commutator cycles. So what is it? The situation is if you have a picture, let me make a new picture. Maybe I make it here. If we have a cycle L0, here we have a cycle L1 and L2, then if we take a cycle which is the commutator of the two cycles which somehow wind around the two separatrices, and we lift it in the foliation. This is a closed cycle. This is the Pochhammer cycle. So this is a commutator of two cycles of the lift of two cycles in the basis. And what is somehow very important here, this is something that we used a lot in a paper with Marcin Bobienski, who is here, is that if we use, so in the work of Ilyashenko, he uses monodromy. And here we use, as in the paper with Marcin, in addition to monodromy, we use weighted variation. And weighted variation of a cycle will produce such Pochhammer cycles. And so these Pochhammer cycles will play the role of somehow vanishing cycles in the work of Ilyashenko. And so as we have an integral which is equal to 0, by continuous extension, we have that the integral vanishes on these Pochhammer cycles. And this will somehow permit to propagate globally somehow the vanishing of an integral at a certain point on one cycle somehow globally. I think I have to stop. So.
Any question? Those specialists in logarithmic foliation. Maybe before, I think you can control the degree of P and R, these polynomials involved.
The what?
Degree of the ingredient.
Yes. I think in the preprint it is not. In the last version of the preprint, it was not. The control was not there, but we can control it. Yes.
Okay. If there is no question, let's thank and then the speaker, and in 10 minutes we are back.